This is a separation vector, right? It's the separation between two particles. If you have two particles falling in, these are trajectories, not world lines. They're just falling in straight in towards the center of the planet, and we take the separation vector. Okay, time is increasing in this direction in the sense that the particles are moving down. Okay, we're going to see just two straight lines. Doesn't tell us anything. If you go towards world lines, we'll see something a lot more informative. It's also the separation between two world lines, which is a little bit of a different thing. It's the same measure, separation between two particles, or if you look at it as two world lines and you're looking at the separation. Same thing because the separation is along the r-axis. Here's r, here's t going up in this direction. We'll have two world lines. Now what will happen is as the particles separate, right, time is increasing in this direction, so they're moving along r. In other words, they're radially infalling. Okay, they're moving straight along the r, but moving along in time, so we have this two-dimensional graph. Now, these two world lines would be diverging from each other. Why? Basically, at each moment in time, let's say at this moment in time, one particle is here at this point in r, another particle is here at this point in r. All right? This is the r separation between them. Right? Don't be misled by this diagram to think that this is a separation like this. All right? Here we have a separation of radial, of angle. Okay? And now what I'm going to look at is two particles moving along a radial line, where one is closer and one is further, and they have an r distance between them. And the psi vector will now be vertical, so to speak, along the radial line. At one moment, when they're beginning their descent, they're pretty close towards each other. At the next moment, they're a little further away from each other because the lower one is being pulled by greater acceleration. At the next moment, they're even further away from each other because the bottom one has been accelerating and therefore has picked up greater velocity and therefore has covered more distance. Okay? So if we plot this with time going in this direction, we can move these arrows over kind of like over here. And here we have that radial separation, the distance along the radial line, distance along the radial line, distance along the radial line, it's increasing. So we can see that the particles moving away from each other like this translates in the diagram to two world lines where they're diverging, where this horizontal, so to speak, distance, which is at a particular time, the distance between the two r's, increases. That's the kind of thing that we wouldn't expect to see in straight lines. This, if you have two straight lines, just the trajectories, right, there's nothing wrong with two trajectories converging or diverging from each other. The way to really see it is to plot this distance as a function of the parameter along this curve. All right, to see how much this changes as you move up the curve. If it changes linearly, if every time you move up a little bit on the curve, it gets 50% more, and you move it up the curve, it gets 50% more, that's a linear change. That would mean that the distance between them is changing linearly, which means that there's a speed difference between them, that's all, not an acceleration difference. But if you plot it and you find that the distance is not increasing linearly between them, then that means that there's a relative acceleration between them. And that's what we would call a deviation, okay, as opposed to just spreading apart. They're deviating from each other, there's relative acceleration. The parameter that we're going to choose along this, we'll call it tau. All right, it's a good parameter, something like the proper time in a watch or free fall particle. You get a relative deviation. Okay, so that gives us some kind of a relative curvature. But that gives you more of an absolute measure of what's happening. Okay, so you can look at it both as a relative and absolute, but it's giving you a more correct version of what's happening because the Riemann curvature this psi is a relative feature. It has to do with two different world lines, right? Its second derivative is a relative acceleration. It's not just an acceleration. One is a relative acceleration. It's telling you the relative motion of the two, as opposed to r.Not by itself, which is an individual acceleration. So that's a very important difference. It gives you a measure of the Riemann curvature, rather than just the connection curvature. Okay? Now, we have various levels at which we're going to look at this. This is a separation vector, right? It's the separation between two particles. It's also the separation between two world lines, which is a little bit of a different thing. It's the same measure, separation between two particles, or if you look at it as two world lines and you're looking at the separation. Then we're going to think of it in terms of worldline deviation. In other words, the kind of thing that would happen only when there's relative acceleration and would not happen when there's only relative worldline deviation. Doesn't tell us anything, you know, watch it, world lines, which are just tidal accelerations in Newtonian gravity. Or eventually we're going to call it geodesic deviation.